The era of cooperative, peaceful space exploration has officially ended, replaced by a ruthless, multi-billion-dollar infrastructure race between two global superpowers. While the American public focuses on private billionaire vanity rockets, the Chinese government is quietly executing a multi-decade master plan to permanently claim the most valuable real estate in the solar system. Every fiscal year, NASA's trajectory is dictated not by mission control, but by the shifting tides of Congress. Appropriations tables reveal a pattern of multi-year rescissions and mid-project funding freezes that have repeatedly derailed long-term planning. In 2010, the Constellation program was terminated after billions had already been spent on hardware and systems integration. The Mars Direct architecture, once the centerpiece of United States ambitions, was quietly shelved after a series of budget writers forced the agency to abandon its surface habitat studies. In 2017, a $350 million cut to planetary science led to contractor layoffs at JPL and the immediate suspension of advanced in situ resource utilization prototype work, delays that ripple through the entire launch cadence. The volatility is structural. NASA's annual budget is subject to the whims of election cycles, committee markups, and last-minute continuing resolutions. GAO reports from 2015 to 2023 document a persistent inability to guarantee funding beyond a single presidential term. This instability translates directly into programmatic risk. The Artemis lunar campaign, for example, has seen its Mars-forward elements postponed or redefined with each new administration. Contracts for heavy-lift SLS boosters, deep space habitats, and nuclear propulsion demonstrators are routinely renegotiated or deferred, leaving critical infrastructure half-built and technical teams in limbo. The consequences are measurable. Between 2012 and 2022, NASA initiated and then canceled or restructured no fewer than 6 separate Mars surface habitat studies. Each termination triggered a cascade of layoffs across prime contractors and subcontractors, eroding the industrial base and draining technical expertise. Congressional writers have targeted specific line items, such as the Mars Sample Return Lander or the Kilopower nuclear surface reactor, forcing abrupt shutdowns even after hardware was fabricated. This stop-start dynamic stands in stark contrast to a rival that operates under a single-party mandate, insulated from legislative turbulence. The United States cadence is not just slow, it is unpredictable. For a race measured in decades and trillions of dollars, cadence risk is not an abstraction. It is a competitive handicap that shapes the balance of power before the first rocket ever leaves the pad. China's Mars campaign is not subject to the turbulence of electoral cycles or the whims of parliamentary budget committees. In 2021, the State Council's 14th five-year plan established a binding mandate for deep space exploration, with explicit language prioritizing a crewed Mars mission in the early 2030s. The 2033 landing date, while never etched into a single public decree, appears as a fixed waypoint in internal CNSA roadmaps and procurement schedules. This target is reinforced by the 2024 National Space Science Roadmap, which lists human Mars exploration as a strategic milestone, and by a cascade of budget allocations that extend well beyond the typical 5-year window. The mechanics of this directive are engineered for continuity. The CNSA, operating as a unified block with the China Aerospace Science and Technology Corporation, executes a disciplined funding model. State Council allocations are not subject to annual renegotiation. Instead, multi-year budget lines are locked in through the National People's Congress, guaranteeing uninterrupted cash flow for launch vehicle development, deep space habitats, and nuclear propulsion. The 2026 state budget earmarks 22 billion yuan over 3 years for the dual-launch Mars campaign, with parallel lines for heavy-lift booster procurement and high-thrust engine fabrication. These allocations are not aspirational. They are binding, enforceable, and backed by the full weight of central government authority. The result is a program cadence that is immune to the stop-start pattern seen elsewhere. Production of the Long March 9th heavy lift vehicle is scheduled at 1 booster per year, beginning in 2028, with supporting infrastructure at the Wenchang Launch Complex already expanded to accommodate the mass and complexity of Mars-class payloads. The procurement of high-energy propulsion systems, autonomous habitat modules, and deep space relay satellites is synchronized across civilian and military supply chains, ensuring that every critical component arrives on time and at scale. This is not a race to plant a flag. It is a methodical, state-directed buildup of interplanetary industrial capacity, with a 2033 crewed landing as the non-negotiable objective. The United States faces not just a rival, but an adversary executing a playbook that eliminates uncertainty at every stage of the Mars logistics chain. Wenchang's transformation is unmistakable. Satellite imagery from 2022 through 2025 documents a sprawling expansion along the southern coast of Hainan, concrete poured for the new Pad B2, a mobile service tower rising beside the original launch pads, and a 2-kilometer rail spur slicing through mangrove swamps to deliver booster stages direct from CASC's inland factories. The hard stand supporting Pad B2 is engineered for the 8,000-ton Long March 9, a rocket designed to lift 140 tons to low Earth orbit and 30 tons to trans-Mars injection. This is not speculative architecture. The reinforced flame trench, the 12-meter integration hall, and the adjacent logistics port are all visible in state media flyover footage and confirmed by open-source geospatial analysis. Procurement notices posted to the Ministry of Industry and Information Technology's portal in early 2025 call for high-thrust cryogenic engines and 100-ton payload adapters, components that only fit the LM9 profile. In Hunan, CASIC's new cryogenic engine foundry is already delivering YF-100 and YF-115 engines at a rate sufficient to supply both the civilian Mars campaign and the PLA's parallel missile modernization drive. The dual-use supply chain is not an accident. It is a deliberate fusion of civilian and military logistics, reducing cost per unit and accelerating technology transfer. The 2026 state budget earmarks 22 billion yuan over 3 years for Mars launch vehicle production and high-energy propulsion, with explicit quotas for annual booster output. CASC's planners have committed to a cadence of 1 LM9 per year, starting in 2028, with the first 2 units reserved for the Tianwen 3 Mars sample return and the dual launch crewed campaign. The integration hall at Wenchang is staffed by a joint CNSA and PLA team, operating under a 2024 directive that assigns range safety to the rocket force and all vehicle assembly to CASC. This command structure eliminates the coordination failures that have plagued Western launch campaigns, streamlining the flow of hardware from factory to pad to orbit. Heavy lift readiness is not theoretical. The logistics rail spur can deliver 6 LM9 core stages per year, and the port expansion allows for barge transport of oversized payloads direct from coastal assembly plants. Each component is tracked and scheduled in a unified supply chain management system, removing bottlenecks and synchronizing delivery with the National Mars mission timeline. The physical infrastructure at Wenchang is the backbone of China's Mars ambitions. It is a launch pipeline engineered for scale, redundancy, and uninterrupted cadence. While the United States debates appropriations, China is building the launch pads, fueling depots, and logistics corridors that will define the next century of off-world competition. China's nuclear thermal propulsion program is built for speed and scale, with technical reports from CASC and the Institute of Nuclear Physics and Chemistry describing a solid core reactor capable of 25 kilonewtons of thrust and a specific impulse of 850 seconds. The reactor, fueled by uranium nitride and protected by silicon carbide cladding, operates above 2000 Kelvin. Hydrogen propellant moves through a porous ceramic matrix, maximizing heat transfer while avoiding pressure loss. Ground test results from the 2025 CFDR campaign confirm stable operation at 3 megawatts thermal, with neutron flux and material durability on track for engine integration by 2028. At a specific impulse of 850 seconds, the logistics become clear. A Mars vehicle carrying 30 tons of payload can achieve over 5 kilometers per second delta V's with 10 tons of propellant, cutting the Earth to Mars journey from 180 days, standard for chemical rockets, to about 115 days. For lighter, 2-ton payloads, the same engine could theoretically manage a 70-day transfer, but real-world constraints, like shielding and mass fractions, push the operational window closer to 100 days. The much-publicized 39-day Mars transit, often cited in media, does not hold up under scrutiny. Achieving such a window would require at least 13 kilometers per second, delta V, and a mass ratio above 4.8, far beyond what current 25 kilonewton engines and available shielding can support. No peer-reviewed analysis, Chinese or Western, supports a 39-day transfer with existing hardware. The real impact is cadence. With a reliable 115-day transfer, China can rotate cargo and crew to Mars nearly twice as often as chemical propulsion allows. Each nuclear-powered vehicle multiplies supply runs, delivering infrastructure, ISRU equipment, and habitats at a pace chemical rockets cannot match. This turns speed into a logistics advantage, supporting the buildup of surface assets and pre-positioned depots before any rival can respond. Risks remain. Regulatory filings from the Ministry of Industry and Information Technology show that China's 2023 space nuclear regulation requires dual-path safety certification for civilian and military launches. The rules demand that unburned fissile material after an abort stay below 0.1% of the initial load, a standard not yet met in full-scale tests. Shielding mass and neutron flux are unresolved for crewed missions, and core components remain at TRL-5, with flight validation not expected before 2030. A catastrophic failure would trigger international fallout, with no precedent for remediation under the Outer Space Treaty. Despite these gaps, China's NTP program is a calculated move to turn propulsion speed into logistics dominance, aiming to secure a permanent self-reinforcing presence on Mars before any competitor can respond. Autonomous excavation units touch down first, targeting the Utopia. Planitia region, where Zhurong's ground-penetrating radar confirmed subsurface voids and high ice content. Swarms of robotic diggers, each pre-programmed with topographic and seismic maps, descend into identified lava tube skylights. Their mission is not exploration, but construction, removing loose regolith, stabilizing tunnel walls, and mapping the geometry of the underground network with LiDAR and magnetometry. Within hours, additive manufacturing rigs follow, deploying mobile gantries that extrude sintered regolith into interlocking blocks. The process uses microwave and laser sintering to fuse Martian soil at temperatures above 1,200 degrees Celsius, producing basalt-based concrete with compressive strength rivaling Earth-grade materials. Layers of regolith are deposited along the tube's inner surface, forming a hardened shell that is both load-bearing and radiation-proof. Standardized habitat cross-section is described in Chinese technical papers, showing 3 meters of fused regolith, yielding a surface density of 30 grams per square centimeter, enough to attenuate cosmic rays and solar particle events below terrestrial safety thresholds. Automated spray systems inject water vapor to bind dust, while robotic arms install modular airlocks and pressure vessels. All of this is monitored in real time from Tianhe-2 mission control, with machine learning algorithms, adjusting excavation rates, and print speeds to compensate for local variations in geology and ice content. Strategic logic is clear. Underground shelters bypass the need for mass-intensive radiation shielding shipped from Earth. By leveraging in situ resources, China's program can put in place hardened, defensible structures before a single human sets foot on the surface. These autonomous bases are not research outposts. They are the foundation for a permanent Martian logistics hub, capable of resisting both environmental hazards and, if necessary, hostile interference. The result is a hardened beachhead, built by machines, engineered to secure territory and resources in advance of crewed landings. The next phase will see these shelters connected to ISRU plants, converting local ice into fuel and life support, locking in access to the most valuable asset on Mars, propellant reserves. Extraction begins where Zhurong's radar mapped the highest concentrations of shallow subsurface ice, Utopia Planitia, a basin with confirmed water ice at less than 5 meters depth. Chinese ISRU engineers deploy autonomous drilling rigs, calibrated to operate in the low-pressure, minus 60 degrees Celsius Martian environment. Each rig feeds ice directly to a bank of polymer electrolyte membrane electrolyzers, arranged in modular arrays for redundancy and scale. The chemistry is absolute. Every ton of water yields 111 kilograms of hydrogen and 889 kilograms of oxygen under ideal conditions. In practice, field losses and system inefficiencies reduce net output by about 10%. But even so, 30 tons of ice can supply enough hydrogen and oxygen to refuel a 30-ton ascent vehicle for a full Mars-to-Earth round trip. Power demand is relentless. Electrolysis at Martian pressure draws approximately 58 kilowatt-hours per kilogram of hydrogen produced. To maintain a viable logistics chain, each electrolyzer array operates at a baseline of 200 kilowatts, matching the scale proven in NASA's Miru and Cryophil prototypes, but implemented here as a permanent nuclear-powered installation. With this configuration, a single array produces about 3.4 kilograms of hydrogen and 10 kilograms of oxygen per hour, consuming 31 kilograms of water in the same interval. Over a 24-hour cycle, that output can fill a 4-ton propellant depot in less than a week, providing the fuel reserves necessary to support continuous vehicle rotations and emergency aborts. Engineers monitor stoichiometry and mass flow in real time, using thermal and chemical sensors to detect ice purity, cell voltage drift, and hydrogen boil off. The entire process is hardened against sabotage and environmental failure, with backup arrays on separate power buses and fail-closed valves isolating each production line. Every kilogram of hydrogen and oxygen produced is tracked as strategic inventory. Fuel not just for ascent vehicles, but for power cells, life support, and, if required, denial operations. Control of these reserves is the linchpin of Mars surface logistics. Whoever owns the propellant controls every launch window, every surface sortie, and every lifeline back to Earth. The calculus is simple. Without local fuel, no rival can sustain a presence, let alone contest the territory. China National Space Administration's Shihei constellation is engineered for autonomy and denial. The Shihei constellation, set to deploy 12 satellites in highly elliptical orbits around Mars, forms a sovereign data corridor that bypasses the US-controlled deep space network. Each node is hardened for continuous encrypted bandwidth between the Martian surface, lunar relay points, and ground stations in Xinjiang and Hainan. This network is not just for mission telemetry. It is the backbone for real-time command of excavation robots, in situ resource utilization plants, and defensive systems. People's Liberation Army communications units oversee encryption protocols and frequency hopping routines, ensuring that no rival can jam or intercept operational traffic. The same infrastructure that guarantees command and control also enables industrial leverage. With exclusive high-capacity relays in place, China can coordinate mining, manufacturing, and logistics chains on Mars without outside interference. The economic implications extend beyond the Red Planet. China already controls roughly 90% of global rare earth element exports. A Martian outpost, backed by autonomous relay links, positions Beijing to dictate access to future off-world resources, rare metals, volatiles, and manufactured propellants. The logic is simple. Whoever owns the communications owns the supply chain. In a denial scenario, rivals could find themselves cut off from both data and critical materials, forced to negotiate for access to the next century's industrial lifelines. Pentagon scenario planners map out 3 operational standoffs. In the first, a U.S. Mars vehicle requests refueling at a Chinese controlled propellant depot near Utopia Planitia. The reply is a flat refusal. Depot access is restricted to mission partners only, citing technical capacity limits. The American crew must either abort or risk stranding on the surface, with no alternative fuel supply within reach. In the second, a Mars surface team attempts to uplink critical telemetry using the Shihe relay network. Chinese controllers deny bandwidth, invoking network security protocols and redirecting all non-CNSA traffic to a low-priority queue. The resulting blackout severs real-time command for excavation robots and aborts remote medical consults, effectively paralyzing operations. In the third, Beijing offers a diplomatic olive branch, conditional access to water ice and comms relays, but only if the US agrees to joint oversight of all surface sorties and shares telemetry in real time. The terms are clear: cooperate or lose the ability to launch, communicate, or even survive on Mars. Each vignette is not hypothetical. These are codified in recent defense doctrine as access denial contingencies, designed to force rivals into reactive, subordinate roles across every logistical and communications axis. Right now, China's state-driven Mars architecture advances with uninterrupted funding, autonomous robotics, and nuclear propulsion years ahead of United States schedules. If Beijing controls ice-based fuel reserves and orbital communications relays by 2033, the United States faces strategic exclusion from the next critical supply chain for interplanetary resources. In this calculus, the first permanent Martian foothold is not exploration. It is the foundation of a new era of power projection. The window for response is closing.